Hello, this is Mr. Pruitt, and today we're going to talk about the mass defect and some applications of nuclear decay and nuclear energy. If you recall, we talked on Friday about about different forces and about nuclear decays. And so here's a quick review of some of the things that we talked about there. And the first one was that atoms have mass. Uh, that they're made of matter and that they take up space and that they have a mass. Um, Atoms of elements have a specific number of protons, and this is their atomic number, and that they also have an atomic mass, which is attributable to the protons and neutrons in the nucleus, um, and to a very, very, very small extent, the mass of the electrons in the electron cloud. Now, that mass may vary because mainly because there may be more neutrons uh, than we would find in a normal atom of that element. And that variation in neutrons, whether it has more or less, we call those isotopes. You need to remember that large atomic nuclei are considered to be unstable because that's due to the very short distances over which the nuclear strong force is effective. Remember that the nuclear strong force is very, very strong, but it's only within very, very small distances. And when we start getting to larger nuclei, the distances between protons can become larger. Also remember that the nuclear weak force is responsible for nuclear reactions and nuclear decay. Alright, so in 1896, Henry Becquerel, who was the person that discovered radioactivity, found something interesting. And what he found was that if you added up the masses of all the protons and neutrons in the nucleus of an atom, then you should arrive at the actual nuclear mass of the atom. And that makes sense. If I took all the protons and neutrons and electrons and I added all that mass up, I should get the mass of the atom. But when we actually measured nuclear mass, these atomic masses or these nuclear masses, the actual measured mass kept coming out less than the sum of its parts. And if you look over here at the picture on the right, looking at this deuterium atom, you notice that it has one proton and one neutron and one electron. And when you add that all up, it comes out to about 2.016 atomic mass units. But the actual mass of the atom is 2.014 mass units. So there's a defect. There's a difference in the mass of the atom and the mass of its actual parts, and we call that the mass defect. And in this case, it's been calculated at about 0.00238 atomic mass units. Now, this difference in the actual mass of the parts and the measured mass is what we call the mass defect. That's our definition. And there was a problem with it because if we really go with the idea of conservation of mass, then the sum of the parts should be equal to the mass of the atom, and this defect created a problem. But in 1905, Einstein proposed a solution for the problem of the mass defect, and basically the solution was contained in his mass energy equivalency equation, which is probably the most well-known physics equation in the world, which was the E equals mc squared equation. Now, this was an equation that's based on relativistic ideas. It's based on speeds approaching the speed of light, momentum and energy as it approaches the speed of light, and explains that basically the idea here is that this equation explains that mass and energy are the same thing, that energy can be converted into mass, and that mass can be converted into energy, and we see that especially now with the identification of the Higgs boson at the Large Hadron Collider. Now, the difference in the mass of the particles can be, and the mass of the atom itself can be found in the energy used to bind those particles together in the nucleus. If you look at this picture up here on the right, you can see where if we had two hydrogen atoms, and then we were to basically smash them together into a helium atom, there would be some energy that's released that's required to bind those nuclei together into that helium atom. And you will also notice that there's a mass defect between the mass of the two hydrogen atoms and the mass of the helium atom. So what we got from this is that the energy that's released in nuclear reactions, and that includes nuclear fissions and nuclear fusions, is all directly attributable to the nuclear mass defect. So if you really wanted to know how much energy is being released in a nuclear reaction, what you would do is you would substitute the mass defect and the speed of light into Einstein's equation, into the E equals mc squared equation. To put a little bit more light on what's going on the right, in nuclear fusion reactions, and those are reactions like the sun or like the hydrogen bomb, protons, these hydrogen nuclei and neutrons are smashed together, and they form a new helium nucleus, and some energy is released at that point. And that energy, which is accounted for in the mass defect, is released as the result of the fusion of these protons and neutrons into a new helium nucleus. So the picture to the right shows us, to the top right, shows us what happens kind of in a nuclear fusion reaction. All right, so let's look at a way oversimplified problem for using Einstein's equation. Let's say that estimates are that the city of Las Vegas, Nevada uses about 92,600 joules of energy on a summer day. All right, so how much fuel mass, if we could have 100% energy conversion, we could take whatever we're using for fuel and we could change it into 100% converted back into energy. How much fuel mass would be required to meet the city of Las Vegas's energy demand for the month of June, for one summer month? Well, to do that, first we would need to find the amount of energy that's required for that month. And so if it's 92,600 joules a day, we would take 92,600 joules and we multiply that times 30, because there are 30 days in the month of June, which would give us 2,778,000 joules of energy that's being used in that month. And then we would take that number and we would substitute it for the E in Einstein's equation. And then knowing that the speed of light is 3 times 10 to the 8th meters per second, we would substitute that for C. So 2,778,000 joules equals the mass times 3 times 10 to the 8th squared. And if you put this into your calculator, C squared is going to come out to about 9 times 10 to the 16th. 2,778,000 divided by 9 times 10 to the 16th gives us an answer of 3.09 times 10 to the negative 11th kilograms. So it takes a very, if you could have 100% energy conversion, it takes a very small amount of mass to convert into a very large amount of energy. So how could we use this? Well, the primary use of the mass defect is in the production of energy. If you look to the right, you can see a picture of the nuclear reactor plant at Glen Rose, Texas. You can also see a picture of the detonation of a hydrogen bomb. And both of those are places where we see lots of energy. nuclear reactors and nuclear bombs are based on this, on releasing the energy that's accounted for by the mass defect. Now, you need to know that in that nuclear, in that bomb on the bottom, that's actually a fusion reaction, and it is much more powerful. It generates much more power and energy than that nuclear reactor plant up there at the top that's based on a fusion reaction. Nuclear power plants generate electricity through nuclear fission. When we talked about nuclear decays the other day, about alpha, beta, and gamma decays, we really didn't talk about how they're used. And most of the uses of nuclear decay that are prominently used have to do with what they call the half-life of the element. Okay, and remember that a half-life is basically the amount of time that it takes for 1/2 of a sample of some element to fully decay. And so for carbon-14, which is the one you're probably most familiar with, the half-life of carbon-14 is about 5,700 years. And so over the course of 5,700 years, you will half of the carbon-14 isotopes in that sample will decay down to carbon-12. And then over another 5,700, another half will decay. And so we can kind of tell the relative age by looking at these graphs, by looking at the number of carbon-14 atoms there are in a sample. We can kind of figure out the relative age of something. Now, carbon-14 is really only accurate dating out to about 25,000 years. To date things that are older than that, we have to use something with a much longer half-life, like uranium-238 that has a half-life in the billions of years. The other place that we use nuclear decay processes, and this is a more recent thing, is that we use it in some medical imaging, like in thallium stress tests. And you can see the results of a thallium stress test in the image up on the left. Basically, what happens in a thallium stress test is that people are brought in, and they're either hooked up to a pump that pumps adenosine in there to raise their heart rate, or they're placed on a treadmill and given an EKG, and they test what happens to their circulation and their heart rhythm under stress. But in the thallium stress test, after they finish that, they inject them when they reach that level of exhaustion or that maximum heart rate they want to. They inject them with thallium, which is a radioactive substance. Now, what they do with the thallium is they send the people home or to eat or whatever, and they can have them come back about 3 or 4 hours later, and then they put them in a machine to get that detects where the thallium is, and it gives them a good idea of how the blood is perfusing through their body, or if there's any blockages or anything in their hearts or anything, and they can look at this, and they can figure out a whole lot about your heart health and your vascular health. Now, the reason that I brought this up is because the big question here for us would be, well, why did they choose to use thallium? Well, the reason they chose to use thallium is because thallium has a very short half-life. Remember, they're injecting this into you. They want this to be something that's not going to be radioactive for very long. And they also want it to be something that when it decays, it's not going to decay into lead or something that's going to be tremendously poisonous to you, and something that can maybe be passed instead of deposited into your fatty tissues. And so for all of those reasons, but especially because of the short half-life, most of these tests are done with thallium because it only has a half-life of about 6 hours. Anyway, I hope that today was useful for you, and I'll talk to you again next time. Thank you.